would like to work out two questions on Newton's laws of motion to show you how these types of problems can be solved. Here's the first one. In this question, there is a 6 kilogram block which is in contact with a 4 kilogram block on a horizontal frictionless surface, and the 6 kilogram block is being pushed by a horizontal 20 Newton force, as you can see. What is the magnitude of the force that the 6 kilogram block exerts on the 4 kilogram block? Sometimes the misconception is that if you apply 20 newtons on the 6 kilogram, then the same force would be applied on the 4 kilogram, which is not true. Now, in order to find the magnitude of the force, we have to draw the free body diagram. Remember that in a free body diagram, you select the system of interest and look at the forces that act only on that system or that object. So when we consider the 6 kilogram object and draw the free body diagram, there are only two forces that act on it. I've called it A and B just to make it easier. The two forces that act on the 6 kilogram are the 20 Newton force that's applied and the force applied by B on A, pushing back. It's actually a reaction force, which is represented as FAB, which is to be read as force on A by B. So those are the only two forces. And therefore the net force is going to be 20 minus FAB. But by Newton's second law, net force is equal to mass times acceleration. And therefore 20 minus FAB, which is the net force, is equal to mass of the object, which is 6 times the acceleration A. So we are using the mass 6 because that's the system of interest. We are only looking at the net force on the 6 kilogram. Now let's do the same thing for the 4 kilogram object. And you got to draw a free body diagram, and in this case, there is only one force that acts on the 4 kilogram object, and that is going to be the force by A on B, which is written as FBA. So that's the net force, and net force is mass times acceleration. In this case, it would be 4 times the acceleration. Now we have two equations, and we need to know that FBA and FAB are action and reaction. So they are equal and opposite. And since we got FBA as 4A, we can simply substitute the value here as negative 4A, because FBA is negative FAB, right? So negative 4A. So that gives us the acceleration as 2 meters per second squared. And once you get the acceleration, plug it back into this equation, and you will find the force applied on B by A, which is what the question is asking you to do. So I hope you understood that. Now this again shows the importance of drawing free body diagram. Now here is the second question. And in this question, you have a system comprising of two blocks of mass of 6 kilogram and 4 kilogram passing over a light frictionless pulley and a frictionless incline. So there's no friction, absolutely. And there are connecting ropes, there is a 9 kilogram block that accelerates downward when the system is released from rest. And we are asked to find the tension in the rope connecting the 6 kilogram block and the 4 kilogram block. So we are asked to find the tension here in the rope. Here we will look at the free body diagrams, and it's easier to start with the 9 kilogram object because there are only two forces that act on the 9 kilogram object. One is the weight of the object mg acting vertically down, and the other force is the tension through the string acting up. And therefore the net force is going to be mg minus t, which is equal to ma. So the mass is 9, so 9 times 9.8 minus t is 9a. And then you get the equation 88.2 minus t is equal to 9 times a. The next free body diagram that we have to draw is considering the 6 and the 4 kilogram as a system. So we're going to consider them together. And the reason is, we do know that the tension in the string here in this part is the same as here. So we know the tension here is T. Well, that's why we are considering this as one system and setting up the free body diagram. So the forces are tension along the string here, and then the weight of the 6 plus 4, 10 kilogram, acting vertically down. Those are the only two forces, but since the weight is acting this way, we need to resolve it into its components. And you are going to get a component along this direction, which is mg sine theta. So that's mg sine theta. So now we see that the net force along the string is T minus mg sine 30, because theta is 30. So now we can use Newton's second law. Net force is T minus mg sine 30, which should be equal to mass times acceleration. So substituting the value of the mass, which is 10 kilogram again, because we're considering 6 and 4 together, and solving it, we get this equation. Actually go back a step. This is the equation that we get. T minus 49 is equal to 10a. So now we have two equations. One is here and the other equation is right here. So what I'm going to do is, because there are two variables in both the equations, it's a set of simultaneous equations, I'm going to just add this equation with this one. So that's why I'm writing it below that equation, and then add them. When you add them, the plus t and the minus t will get cancelled. And then you have 19a on this side, and then you do the math there, you will get the acceleration as 2.06 meter per second squared. Now we can draw the free body diagram on the 6 kilogram. All right, so the two forces acting on the 6 kilogram here are its weight vertically down and the tension in this part of the string, which is not T. So we're going to call it something else, say T prime. So here is the free body diagram. So you have T prime and mg. Once again, mg is resolved into mg sine theta, which is the only component we need. So the net force on the 6 kilogram is T prime minus mg sine 30, which is equal to m times a. And from here we can surely find T prime because we already got the acceleration of the system. The mass is now 6 because we're only considering the 6 kilogram. Acceleration is 2.06, and then you have mg sine 30. When you do the math, you get 41.76 newtons, or approximately 42 newtons, as the tension in the string between the 6 and the 4 kilogram. So that's how you work out this very important problem. This problem is important because it clearly shows how we need to be smart in setting up free body diagrams and then solving them to find the different unknown forces. Thank you, and hope you have understood a little bit more than before you watched this video.